transparent layer in the front part of the eye is cornea. Right behind lies the iris. Giving the eye its colour, the iris adjusts its size automatically according to the sharpness of light, thanks to the muscles attached to it. For example, if we are in a dark place, the iris widens to take in as much light as possible. When light increases, it shrinks to decrease the amount of light coming into the eye. The automatic adjustment system in the iris works like this. The moment light comes into the eye, a nerve impulse travels to the brain and gives message about the existence and brightness of the light. The brain immediately sends back a signal and orders how much the muscles around the iris will contract. Another eye mechanism working parallel to this structure is the lens. The duty of the lens is to focus the light coming to the eye onto the retina layer at the back of the eye. Thanks to the movement of the muscles around the lens, light rays coming to the eye from different angles and distances can always be focused on the retina. All the systems we have mentioned are far smaller, yet far more superior to the mechanical devices designed by the use of the latest technology in order to imitate the eye. Even the most advanced artificial imaging system in the world remains extremely simple and primitive compared to the eye. When we think of the effort and knowledge that has been put into developing these artificial imaging systems, we can understand with what a superior creation the eye is made. If we examine a single cell in the eye at the microscopic level, the superiority of this creation will be further revealed. Let us suppose that we look at a crystal bowl full of fruit. The light rays coming from this bowl to our eye pass through the cornea and iris and are focused on the retina by the lens. So, what happens in the retina so that the retinal cells can perceive light? When light particles, also called photons, strike the cells in the retina, they produce a cascading effect like a row of dominoes carefully arranged one after the other. The first of these dominoes in the retinal cells is a molecule called 11-cis-retinol. When a photon of light interacts with it, this molecule changes shape. This forces a change in the shape of another protein, rhodopsin, to which it is tightly bound. Now, rhodopsin takes such a form that it can stick to another protein called transducin, which was already present in the cell, but with which it could not interact before due to its shape's incompatibility. After this union, another molecule called GDP also joins in this group. Now, two proteins, rhodopsin and transducin, and a chemical molecule called GDP have bound together. However, the process has just begun. The compound called GDP now has the proper form to bind to another protein called phosphodiesterase, which always exists in the cell.